Swayam Prabha. Digital India. Educated India.
Welcome to a new module. The module is on Gaussian distribution. But before I continue, I would like to be able to recollect why we are doing what we are doing on Gaussian distribution. If you recall, the title of the course is Mathematics for Data Science. Mathematics for data science come from various directions: theory of vector spaces, matrices, multivariate calculus, optimization, numerical analysis, probability theory, statistics, a good facility programming. These are all the fundamental basics, tools that one needs to pursue a serious work in data science. We have already covered vector spaces, matrices, multivariate calculus, optimization. We are not giving lectures on probability theory, but within probability theory, Gaussian distribution plays a very central role. So, to fill this gap of not covering the probability theory in full, I am going to cover many of the standard properties of Gaussian distribution. So, that will help us to be able to provide some good background in some of the probabilistic properties of Gaussian distribution. Later, after finishing this, we will also talk about basic principles of statistical estimation. Again, we are not planning to cover the entire estimation theory. We are going to get some glimpses into estimation theory. So, as a part of topics in probability theory, I am going to cover Gaussian distribution. So, what are the topics to be covered? Properties of Gaussian distribution, computation of moments. Gaussian density has a very particular property, namely uncorrelation implies independence. In vector algebra, we talked about linear independence. Here we are talking about statistical independence. We are also going to be talking about conditional distribution, which is another fundamental property in probability theory. So, the standard Gaussian is given by X as the mean m sigma square variance. So, X is a random variable. X is normal with mean m sigma square variance. The functional form of the normal distribution is given by this 1 over square root of 2 pi sigma exponential minus x minus 1 whole square by 2 sigma square. That is called the probability density of the Gaussian distribution. It is uniquely described by two parameters, m and sigma square. M is called the expected value of x, that the mean is the location parameter. Sigma square is the variance of x is sigma square. By definition, variance is equal to expected value of x minus m whole square. Variance describes the spread. Now, if I subtract m from x and divide it by sigma, if sigma square is variance, sigma is called the standard deviation. This ratio is called the standard normal random variable. The standard normal variable has a property, is the mean 0, variance is unity. Subtracting the mean in probability is called centering. Multiplying or dividing a random variable by a quantity is called scaling. So, Z is a centered, scaled version of the original random variable. So, I can convert a random variable with arbitrary mean and arbitrary variance to standard normal variable with a mean 0 and variance 1. So, P of Z is normal 0, 1, this is 1 over square root of 2 pi. exponential minus z square by 2. So p of x here, p of z is here, x is a general normal random variable, p is a standard normal random variable. So that's the difference between x and z. The first property is that the integral of the probability density function is 1. I'm now going to show you how to prove that the integral from minus infinity to plus infinity of p of x dx is 1. So that's the title in here. I is equal to integral of minus infinity to plus infinity p of dx is 1. To show that, what is that we are going to do? I'm going to consider I square, which is the product of I with itself. So this is I, this is I again. X is the variable of integration. So here the dummy variable x, here the dummy variable is y. So if I substitute for px, py, I am computing I square is 1 over 2 pi times sigma square, double integral exponential this x minus m by sigma whole square plus y minus m by sigma whole square dx dy. There is a minus half factor that multiplying the whole thing. Now I am going to change the variable. X minus m by sigma is r cosine theta, y minus m by sigma is equal to sine r sine theta. R is a non-negative quantity. It goes from 0 to plus infinity, and the angle theta is from 0 to 2 pi. So x and y going from minus infinity to plus infinity implies r is a non-negative quantity, non-negative real quantity, and 0 and theta is restricted to 0 and pi. Dr dx then becomes sigma square r dr d theta. Dx dr is an elemental area, the rectangular elemental area in the original coordinate system. Sigma square r dr d theta is the magnitude of the same elemental area in the polar coordinate system. So I am trying to change the variable from Cartesian coordinate to polar coordinates. And change of coordinate system you must be very well familiar with in your calculus course. So I have converted the Cartesian representation to a polar representation. In here, I square now becomes 1 over 2 pi, 0 to 2 pi d theta, 0 to plus infinity r e to the power of minus r square by 2. The reason I am trying to express this because I want you to be able to recall some good practice in integration. So earlier, x and y were involved, combined. So in the double integral, x and y is changed into r and theta. If we express this in the polar form, the double integral is now in a separable form, one integral involving theta, another integral involving only r. I can evaluate these integrals separately. It is the separability property is what we are interested in. And this is something you must be familiar with. In integration theory, integration of complex integrand can be simplified by change of variables. That's exactly the same trick. So now I'm trying to evaluate each of the integral. The r integral is 0 to infinity r e to the power of minus r square by 2 dr. This can be evaluated. This can be rewritten like exponential minus r square by 2 d of r square by 2. Though this is like e to the power of integral of e to the power of x dx. So that is minus of exponential minus r square by 2 from minus 0 to plus infinity, that's equal to 1. The first integral with respect to theta is 0 to 2 pi is 2 pi, but 1 over 2 pi is a factor that's coming in here, 2 pi gets cancelled. The second integral evaluates to 1, therefore I square is 1, therefore I is 1. If I square is 1, I can be plus or minus 1, but the integral of the probability density is plus 1, therefore I is 1. Therefore, how do you verify the total probability mass from minus infinity to plus infinity for a normal distribution with mean m sigma square variance equal to 1? That's exactly what I am trying to help you to visualize. And compute, and also I'm trying to tell you some of the tricks that are used to be able to do this arithmetic. Now I want to be able to verify that the expected value of x is m. Either you can believe or you can verify, and we can verify. I believe, I also want to be able to verify. So the expected value, you all know expected value of x is integral x px dx. Therefore, 1 over square root of 2 pi sigma x probability density function that is given in here. I am adding and subtracting m. This is a usual mathematical trick. So I am expressing this one integral into two integrals. One is x minus m times the probability density function. Another is m times the probability density function. M is a constant. M gets out of this. If m gets out of this 1 over square root of 2 pi sigma exponential, that's essentially the probability density function, which I have already shown is 1. So the second term in this page is 1. The second term is equal to 1. Now I am going to prove that the first term vanishes. To that end, I am going to define f of x, which is equal to the integrand. The integrand is x minus m exponential minus x minus m whole square divided by 2 sigma square. This function, as a function of x, is called an odd function. A function is said to be an odd function if f of x is equal, if I change the sign of the variable x to minus x, f of x changes the sign. So what is an example of an odd function? X cube is an odd function. What is the even function? F of x is equal to f of minus x. If f of x is equal to f of minus x, then it's called even. If f of x is equal to minus of f of minus x, that means changing the sign of the argument changes the value of the function. So if y is equal to x cube, y at minus x is minus x cube. If y is equal to x square, y at minus x is also x square. So the integrand in the first integral is an odd function. This integral is from minus infinity to plus infinity. I can split it into minus infinity to m and m to plus infinity. Minus infinity to m can be written as minus of m to plus infinity. You all should know that. Therefore, I have two integrals. Both are equal but opposite in sign. The sum is 0. The second integral has been evaluated to be m. So expected value of m, expected value of x is m. Now I am going to prove that the variance of x sigma square, again, is a very simple but interesting exercise. Variance of x is equal to expected value of x minus m whole square. That's equal to 1 over square root of 2 pi sigma minus infinity plus infinity x minus m whole square, the probability density function. Probability density function. Now I am going to consider the integral. I'm calling it I1. I'm going to consider the integral separately to be able to evaluate. To be able to evaluate. So now you can readily see this integrand can be expressed as x minus m times d of that. That's again a standard way in integration theory. Now I am going to express this integral as two parts. I1 is equal to I1a and I1b. I'm going to show you all the basic steps. That's the idea. So computation of the variance continues. I1a is minus sigma square times x minus some exponential, the term, the standard density term, minus infinity plus infinity, I am trying to integrate by parts. I am using integral uv is equal to uv minus v du. So this is the uv part evaluated from minus infinity plus infinity, that you can verify it to be 0. The I1b, the second part of the integral, again, sigma square gets out. This is the standard normal Gaussian functional form. You know the integral from minus infinity of this, when multiplied by 1 over square root of 2 pi sigma, is 1. Therefore, this integral is equal to square root of 2 pi sigma. So, substituting back in all this, we simply get the variance to be equal to sigma square. So, you can readily see I have split this computation in slide 8 as two sums. One is both the parts coming from integration by parts, and I have helped to evaluate both the terms to show it is sigma square. Now, there are two types of moments. One is called central moment, another is called uncentered moment. Mean is the first uncentered moment, variance is the second centered moment. So, integral of x to the power k px dx is called the kth moment. Integral of x minus m to the power k px dx is called kth central moment. Both the moments are interesting and important. So, mean is the first non-central moment. Variance is the second central moment. I can compute the third moment for the normal distribution. It is 0. I am showing the actual calculation. E of x minus m whole cube is given by this integration. Now I am going to consider the integrand to be a function of x, f of x, and there is an odd function with respect to the odd function of x with respect to m. The odd function with respect to m can be split into minus of m to plus infinity plus m to plus infinity, which that same trick I have already used in the earlier slide when I had computed the mean. So verify the third central moment is 0 because it's an odd function. The integral of the odd function from minus infinity to plus infinity is 0. Likewise, verify that the odd central moment E of x minus m to the power n, when n is odd integer, is 0. So that's a very good exercise for you to be able to test your understanding of these integrals. Fourth central moment. In the case of Gaussian, the fourth central moment is E of x minus m to the power 4. I'm going to show its value is 3 sigma to the power 4. In statistics, the third moment is related to skewness. Fourth moment is called kurtosis. These are special terms. So the mean, variance, skewness, and kurtosis. These are related to the first 4 moments. So I am now going to evaluate the fourth central moment and show it is 3 times sigma to the power 4. Consider the integral I of 2, which is given by this integral except for the multiplying constant here. So I of 2 is equal to minus sigma square. I can rewrite this in this particular form. So this is the form u dv. So I can rewrite this by applying the rules of parts, integration by parts, u dv minus v du. So integration by parts essentially tells you I2 is given by the sum of these two terms. I have to evaluate these two terms independently. The first term is going to be 0. The first term vanishes. Why first term vanishes? Is because first term vanishes because this function is an odd function. And I am trying to evaluate it from minus infinity to plus infinity. and please verify the first term is 0, the second term, the integral of the second term is simply sigma square. So I'm going to get it 3 times sigma to the power 4. So the second term is 3 times sigma square times 1 square root of 2 pi sigma. Please understand, I have that constant coming in, I'm going to substitute that. Therefore, combining E of x minus m to the power 4 is 1 over 2 pi sigma I2, which is 3 sigma square. Continuing this way, we can essentially verify expected value of x minus m to the power n is 1 times 3 times 5 times n minus 1 times sigma square to the power n by 2. You all know factorial. Factorial is 1 times, 2 times, 3 times, 4 times. But given an n, I am simply multiplying all the odd numbers that are less than n. So that is denoted by n of 2 factorial signs. N of 1 factorial sign means every product of every integer from 1 to n. The 2 factorial signs means it is a product of every integer, every odd integer less than or equal to 1, less than or equal to n. Therefore, when n is even, this double factorial is essentially 1 times, 3 times, 5 times, 7 times, all the way up to n minus 1. So, what is that now I have shown so far? For the general Gaussian density, I have proven that the total area must be 1. You all know this, but the whole question is this. Do you know how to prove it? That's what I'm trying to do. In that process, you are also learning a good bit of manipulations, mathematical manipulation, which will essentially help you. And what are the various things I have used so far? The integral of an odd function is 0. That's one fact. The second fact, what is that I have used? I'm going to use integration by parts. So using integration by parts and using the property of odd function, I have now evaluated all the moments, central and non-central moments of the Gaussian distribution. Thus far, we introduced what is the Gaussian density, how do you compute the mean variance, how do you compute various moments, the third central moment, fourth central moment. Third central moment is called skewness, fourth central moment is called kurtosis, second central moment is called variance, first uncentered moment is called mean, and there's a lot of mathematical jugglery that is involved in here. The aim is to be able to get to know these kinds of mathematical manipulations so that you can develop skills in doing these kinds of evaluations. Now I'm going to talk about the following property. We said that Gaussian distribution is distributed from minus infinity to plus infinity. Minus infinity to plus infinity is a huge interval. So I want to find out where the probability measure is concentrated. We are going to see that the large part of the probability measure is concentrated around the mean, even though it is from minus infinity to plus infinity. So I would like to be able to quantify the concentration properties of standard normal density. So here Z is equal to normal 0, 1. The expression for that distribution is 1 over square root of 2 pi exponential minus d square by 2. Oftentimes we talk about standard normal distribution because once we understand the standard normal distribution, I can convert the standard normal distribution to any normal distribution by multiplying it by standard deviation plus adding the mean. So standard normal, understanding the standard normal distribution is absolutely fundamental. So while it is known Z can potentially span over a large interval, a large fraction of this probability mass is contained in a small subinterval centered around the origin. In this case, origin is the mean. So it is well documented from probability tables that from between minus 1 and plus 1, say look at this, this is the probability density function. The value, the integral of this density from minus 1 to plus 1 is 0.683. That means more than 68% of the total probability mass is contained within the short interval -1 to +1. If you change it to -2 to +2, 0.955%, more than 95% of the probability mass is contained between -2 and +2. If you change it to -3 and +3, between -3 and +3, the probability mass is over 99.7%. So between -3 and +3, if it is over 99.7%, please understand, outside of it, from 3 to +infinity, from -3 to -infinity, the total probability mass is less than 0.003, is equal to or less than 0.003. So what does this mean? Even though it is known to spread between -infinity and +infinity, much of the action are centered in a small interval around the mean. This property is called concentration of probability measure. We will have a lot to talk about the concentration later. This is called the extent of the probability distribution. So if I know the extent of standard normal, I can extend it to any mean, any variance. In the previous slides we have already shown, if x is a general normal random variable with a mean m and sigma square as the variance, z, the standard normal, can be obtained by centering and scaling. Therefore, if z is in between -1 and +1, x must be in between m minus sigma to m plus sigma. If z is in between -2 and +2, x will be m minus 2 sigma to m plus 2 sigma. If z is less than or it is in the interval -3 to +3, x will be in the interval x minus 3 sigma to x plus m. X must be m minus 3 sigma to m plus 3 sigma. The same percentage continues. That means for any general normal random variable, more than 99% of the probability mass is contained within the short interval of length 6 -3 to +3 on both sides of the mean, m minus 3 sigma to m plus 3 sigma. So this is called 6 sigma property. With an interval of length 6 sigma centered around m, more than 99% of the probability mass is concentrated. Now I am going to go from univariate, that means x as a random variable, to multivariate. Why multivariate normal is important for us? Because data science is a multivariate science. We need to be able to understand the properties of random vectors. So let A be a n by n matrix, B be a vector, x is a n vector, x is a normal random variable with a mean m and a variance sigma square, and covariance matrix sigma. M is a vector of size Rn, sigma is a matrix of size n by n. X is distributed according to normal distribution, mean m and covariance matrix sigma. The functional form of the multivariate normal Gaussian density is given here, 1 over 2 pi to the power n by 2, determine the square root of the determinant of sigma, exponential minus 1/2 of the quadratic function x minus m transpose sigma inverse x minus m. So the exponent is a scalar because this is a quadratic function. The matrix of the quadratic form is sigma inverse. It is assumed that sigma is symmetric and the covariance matrix is always symmetric. In general, covariance matrix can be positive semi-definite. In this special case, I am going to assume that the covariance matrices are symmetric and positive definite. If it is symmetric and positive definite, sigma inverse exists. So m is called the mean location parameter. Covariance matrix by definition is this. Sigma is the covariance of that. This absolute value of sigma represents the determinant of sigma, and I am assuming sigma is non-singular. Sigma will be non-singular when sigma is symmetric and positive definite. So why am I spending a little time on this? Because you must be able to write down the functional form of both the scalar normal distribution as well as the vector, the normal distribution for the vector random variable. Now I am going to talk about linear transformations of random variables, in particular linear transformations of Gaussian random variables. So let X be a Gaussian n vector, X has a mean m and variance sigma. I am going to transform X to Y by multiplying by A and adding a vector B. So A is a matrix, B is a vector, X is a random vector, Y is the resulting random vector. I am assuming A is a square matrix. So E of Y is equal to E of Ax plus B. E of Ax is equal to A times Ex plus B. This is the A of M plus B. So if X has a mean M, Y as Ax plus B has a mean AM plus B. Covariance of Y is Y minus E of Y times Y minus E of Y transpose. But Y minus E of Y, we already have calculated E of Y in the first line. So Y minus E of Y is essentially A times X minus M. You can readily verify that. Therefore, covariance of Y is equal to E of A times X minus M times X minus M transpose A transpose. That comes from the definition of covariance. So this is equal to A sigma A transpose. So now we can readily see if X is a random variable, normal random vector, the mean M and sigma square, sigma as a covariance matrix, Y is a normal random variable with the mean AM plus B, the covariance is A sigma A transpose. A sigma A transpose. So this is how the behavior of random variables under transformation. Now, when n is equal to 2, when n is equal to 1 is called univariate, when n is equal to 2 is called bivariate. In order to be able to get a good feel for normal distribution in multi-dimension, it is always good to have good understanding of the normal distribution in 2 dimension. X is x1, x2, m is m1 and 2. Sigma in this case can be represented by this, sigma 1 square, sigma 2 square diagonal. They are the variances of x1, x2. The off-diagonal elements are called covariance. That is rho times sigma 1, sigma 2, rho times sigma 1, sigma 2. Rho is called the correlation coefficient. Correlation coefficient is between plus 1 and minus 1. So the determinant of sigma is sigma 1 square, sigma 2 square, 1 minus rho square. So the square root of the determinant is given by product of sigma 1, sigma 2, square root of 1 minus rho square. So the inverse of this 2 by 2 matrix is given by this. Please verify. How do you verify? You multiply sigma by sigma inverse by sigma, you get the identity matrix of order 2. So I have given you all the answers. You simply need to be able to verify to get the practice. So the exponent of the bivariate form is j of x is 1 over 2 x minus m transpose sigma inverse x minus m. I know the value of sigma square inverse. This is the quadratic function. I can evaluate the quadratic function. The quadratic function can be evaluated and expressed as the sum of 3 terms, which is given to the right hand side of 1. Therefore, the bivariate normal distribution P of x is given at the bottom of this slide, which is 1 over 2 pi sigma 1 sigma 2 square root of 1 minus rho square exponential minus jx. So I have a very specific way of expressing normal random variable in 2 dimensions. Now I am going to show x1 and x2 are 2 components of the random vector. If x1 and x2 can be correlated, rho is the correlation between x1 and x2. I am going to set rho is equal to 0 in j of x. If I set rho is equal to 0 in j of x, you can really see the determinant of sigma is sigma 1 square, sigma 2 square. Square root of the determinant is sigma 1, sigma 2. So j of x at rho is equal to 0 is simply x1 minus m1 whole square by 2 sigma 1 square plus x2 minus m2 by 2 sigma 2 square. So I have separated the 2. There is no cross term x1, x2. So if I substituted this in my p of x, I can rewrite this as a product of 2 Gaussians. 1 over square root of 2 pi sigma 1 times this, 1 over square root of 2 pi sigma 2 times that. That's called P1 x1, P2 x2. So what is that we know? If two random variables are independent, their joint distribution is simply the product of the distributions. So in the case of Gaussian, what is that I have now shown? If two Gaussian random variables are uncorrelated, they are also independent. Independent is a very strong property. Correlation is a weaker property. Gaussian density has a special property, namely uncorrelated means independence. Independent means uncorrelated. So for Gaussian random variable, these two concepts are equivalent. In general, for a general random variable, uncorrelated random variable need not be independent, but independent random variables will always be uncorrelated. Therefore, what is the topic of this slide? Uncorrelation. Uncorrelated implies independence. That's a special property of Gaussian density. Now I am going to talk about the conditional density. x1 and x2 are two components of a random vector. P of x is P of x1, x2. The joint density is given by 1 over square. The joint density is given by, that should be, it should be there should be no square root in the first one. So 1 over 2 pi, the Px1, the expression is given by this. Px2 is given by similar expression. Px1, x2 is the joint density. I'm going to show you the joint density is given by in equation, this is joint density in slide 18. So that is 2 pi times sigma 1 sigma 2 times that joint density. So in here there is an error. The error is essentially the square root of sign should not be there. So in the exponential minus j of x. So P1 is equal to 1 over square root of pi sigma 1 exponential that. So this is joint density. This is the marginal density of x1. So the conditional distribution Px2 given x1. Please look at this now. The joint density has a dependence on both x1 and x2. I also know the individual density, the marginal density of x1. So I would like to be able to compute the conditional density. The conditional density is simply simply the ratio of the joint density by the density of Px1. I know the joint density, the numerator, I know the marginal density Px1, I substitute, the expression becomes this expression at the bottom of the slide, that's the expression for the conditional density. Now I am going to simplify the conditional density. I am going to add and subtract rho square x1 minus m1 square divided by sigma 1 square inside the square term in the jx, inside the square term in the jx. So the jx in 1, you already know what it is. I am going to add and subtract. If I did that, minus jx now becomes this long expression. This long expression now can be simplified to be minus jx plus x1 minus m1 whole square divided by 2 sigma square, and that is essentially given by this expression. That is essentially given by this expression, which is within the square bracket x2 minus m2 minus sigma 2 rho divided by sigma 1 x1 minus m whole square. This is the multiplying constant. So now you substitute, combine and simplify the probability of x1 given probability of x2 given x1. I'm sorry, there's an error. This is a probability of x2 given x1. That's what we are considering. This is the right one, x2 given x1. So probability of x2 given x1 is given by this density. The expected value of this now can be denoted by m2 bar, and m2 bar from the previous relation I can easily show m2 plus rho times sigma 2 sigma 1 to the power minus 1 x minus m1. This, when simplified, m2 plus rho times sigma 1 sigma 2 divided by sigma 1 square x1 minus m1, and this can be rewritten as m2 plus covariance of x1 x2 divided by variance of x1 times x1 minus m1. So this is called the conditional mean. The conditional variance, the variance of x2 given x1 is rho 2 1 minus rho square. That's a conditional variance. So I talked about bivariate distribution. I talked about conditional distribution of x2 given x1. x1 and x2 are the only two variables. Now I would like to be able to extend that conditional distribution to multivariate case. In this case, I am going to assume x1 is a random variable of size n, or random vector of size n, x2 is a random vector of size m, expected value of x1 is m1, covariance is sigma 1, expected value of x2 is m2, covariance of x2 is sigma 2. x1 and x2 are correlated, so sigma 1 2 is covariance of x1 x2, sigma 2 1 is covariance of x2 x1. You can readily verify the covariance of 2 1 is the transpose of the covariance of 1 2, and the joint density x is given by x1 and x2. So if I define x to be x1 transpose, x2 transpose, transpose, that means x is a long vector with two components x1 and x2 concatenated. M is the corresponding mean. I am going to define a covariance matrix sigma 1, sigma 2, sigma 1 2, sigma 1 2 transpose, and this is the R m plus n by m plus n matrix. Using this mean, as using this covariance, I can express the joint density of this vector, where x1 is the first top component, x2 is the bottom component, both of them are vectors. So this essentially tells you the joint density of a long vector whose top part is called x1, the bottom part is x2. So I have known the joint density. Now I would like to be able to compute the conditional density of x2 given x1. I want to be able to compute the conditional density of the bottom part given the top part. And I am assuming sigma 1 and sigma 2 are non-singular. Sigma 1 and sigma 2 are non-singular. I am assuming sigma 1 and sigma 2 are non-singular. That means both the random variables x1 and x2 by themselves are well-defined random variables with a symmetric positive matrix for each of them. So x1 and x2 are coupled. I want to be able to, if they are joint density, x1 affects x2, x2 affects x1. So what is that I am interested in finding? If I know x1, how much of the information in x1 is going to affect the probability density function of x2? That's what's called the conditional distribution. And to that end, I had to decouple the covariance matrix. To that, I am going to define a transformation matrix T. The transformation matrix T is a m by n m plus n by m plus n matrix. It's the partition matrix. This is IN, identity function. This is the identity matrix or identity matrix. That the top element on the right hand side is 0. The bottom element on the left hand side is minus sigma 2 1 sigma 1 inverse. I have already assumed sigma 1 and sigma 2 are non-singular. So I already know what sigma is. Please understand, sigma is sigma 1 sigma 2 sigma 1 2 sigma 1 2 transpose. You remember that from the previous. So this is T, this is sigma. If I multiply sigma by T, I get this matrix. Sigma 1, sigma 1 2, 0, then this matrix, sigma 2 plus this matrix. So now you can see if x is the original variable, the transformed variable is called x bar. So x is the original variable, m is its mean, x minus m is the centered original variable, t is the transformation. The transformed variable is given by bar, x consists of x1, x2, x bar consists of x1 bar, x2 bar. x1 bar, so this is the matrix T we already have from the previous slide. This is the vector x1 minus m1, x2 minus m2, that is the vector x minus m. So x1 bar is x1 minus m1, x2 bar is x2 minus m2, minus, so I have to multiply these two. If I multiply these two, please understand, x1 bar is x1 minus m1, x2 bar is x2 minus m2 minus. So I have to multiply the first component by this, second component by this, and add that, and that is equal to x2 minus m2 bar, and m2 bar from this expression you can really verify is m2 minus sigma 21 sigma 1 to the power minus 1 x1 minus m1. Therefore, the covariance between x1 bar and x2 bar, what is x1 bar, x2 bar? It's a transformed vector x. So x had a covariance, I do a transformation, I'm now going to compute the transformation of the transformed variable, the covariance of the transformed variable. So the covariance of this is equal to covariance of x1 minus m1, x2 minus, so this is the transformed variable. You remember that? x1 bar is given here, x2 bar is given here, x1 bar is substituted, x2 bar is substituted. I am trying to compute the covariance between these two quantities. So the covariance between these two quantities is the covariance between x1 minus m1, x2 minus m2 minus the covariance of x1 minus m1 times this term. So in this particular term, this is the matrix. The matrix comes out, and I'm essentially having the covariance of x1 minus m1, and this is exactly relation given by sigma 1 2 minus sigma 1 inverse sigma 1 2 transpose, that is 0. So what is it we have shown? While x was correlated, the transform x, which is x bar, is uncorrelated. So we have a set of x1, x2 which are correlated. Now x1 bar, x2 bar is uncorrelated. So the transformation is essentially try to decorrelate it to two components of x. So x1 bar, x2 bar are uncorrelated, and hence they are independent. Please also remember a formula from probability theory, covariance of AXY, where A is the matrix, x and y are vectors, is A times covariance of xy. Covariance of xay is covariance of xya transpose. These are important formulas that come from the basic definition of the covariance. So now I have the covariance of transformed variable and the distribution of the transformed variable. So x1 bar is x1, but that is normal. x2 bar is x2 minus m2 bar, which is given by this expression, x2 minus m2 minus a part that multiplies x1 minus m1. So covariance of x2 bar is expected value of covariance of x2 bar is x2 minus m2. So this is, look at this now, it's the covariance of this two terms. The covariance of these two terms, when you substitute, it gets into 1, 2, 3, 4. This essentially comes from the standard rule for computing the covariance. And if you actually compute the values of each of these quantities, you can really see these two get cancelled. So we are left behind sigma 2 minus sigma 2 1, sigma 1 inverse, sigma 1 2. So covariance of x bar is T sigma T transpose has to be expected. So we already know how the covariance transforms themselves. If I multiply a Gaussian random variable with a matrix, and that's exactly what the result is. We have already verified that now. So with that in place, I am now going to get the conditional distribution. The conditional distribution, so Px1 bar is the same as Px1, which is normal M1 sigma 1. So I am conditioning an x1. So Px1 is the marginal. So Px2 bar given x1 bar is the same as Px2 given x1, that is equal to normal of M2 bar sigma 2 bar. X2 bar is given by the expression M2 plus some quantity, that's called conditional mean. And this is very important to understand. If you ask for the property of x2 by itself, the marginal, the mean of x2 is M2, the covariance of x2 is sigma 2. But if you compute the conditional distribution of x2 given x1, x2 not only has property it used to have, but also inherits the property from x1. That's what's called the impact of conditioning. So these two added terms, the first one is the term that is added. The second term is also the term added. Addition is subtraction, subtraction is addition. So these are two terms that are going to be affecting the mean and the covariance. Now I want you to verify that these are generalizations of the scalar case. So what is that in summary we have done thus far? We talked about the standard properties of Gaussian density. We proved that for Gaussian uncorrelated is equal to independent. We talked about the transformations of Gaussian random variables. We computed the mean and the covariance and the transformation and computed how the mean and covariance get transformed. Then we talked about joint density, the marginal density and conditional density. This we did it for random variables of size, of the random vectors of size 2, bivariate. I computed the conditional density for a bivariate case. I am now computing the conditional density for a vector case. The matrix algebra is interesting, very important. So there is a mix of both statistical as well as matrix properties involved. It's a very good exercise to be able to understand how matrix theory helps to derive expressions and help to reveal the properties of quantities in probability theory. With that, we come to the end of this. I am going to now give some exercises. Plot P of x. I want you to pick the mean to be -1, 0, +1. I want you to vary the variance 0.1, 0.5, 2, 1, 2 and 5. So you fix the mean, you superimpose 1, 2, 3, 4, 5 variances. So you pick the mean to be 0, compute the 5 distinct densities of the varying sigma, superimpose them. This way you can readily see the impact of changing the variance on the distribution. Then to change the mean to -1, change the mean to +1. So this way you can understand how the function changes if I change the mean, if I change the variance. Comment on the behavior with increasing sigma square. So what is that you should observe? When sigma square becomes larger and larger, the peak at the mean becomes shorter and shorter. The probability mass tends towards larger values. When sigma square is small, the probability densities are peaked. It is this variation of the shape of the Gaussian density, when you change the variance, when you change the mean, is fundamental to basic understanding. Now, the easiest multivariate case is bivariate case. So I am going to consider a bivariate case x is equal to x1, x2. The standard density of bivariate case 1 over 2 pi determinant of sigma to the power half, exponential 1/2 of x minus m transpose sigma inverse x minus m. We already know m is m1, m2. We already know sigmas, the matrix is sigma 1 square, sigma 2 square with rho, sigma 1, sigma 2, the off-diagonal terms. Now I am going to ask you to assume m1 is 0, m2 is 0. Assume sigma square is 1, sigma 2 square is 2. I would like you to be able to vary rho. Now what is that I want you to do? Fine. I want you to draw the contours. What is the contour? A contour is the locus of a point. It is the locus of x where the value of p of x is constant. So if you say p of x is equal to half, what are the values of x for which p of x will be half? What is the value of the vector x1, x2? What are the components of the vector x1, x2 that will render the value of p of x to be half? This I would like you to do when you change the rho. What is rho? Rho is the correlation. Please plot when rho is 0, that's the first case. Then rho is plus 1, rho is minus 1. Rho is plus 5, plus 0.5 minus 0.5, and rho is plus 0.9 minus 0.9. I would like you to be able to plot these things and keep it with you so that you can essentially see how the shapes of various Gaussian distribution change when you change the mean, when you change the variance, when you change the correlation coefficient. And I would like you to be able to comment. I would like you to be able to talk about the orientation of the contours. The contours are essentially ellipses. So where the minor axis, major axis align themselves, I would like you to be able to get a good feel for the various shapes as you vary rho for a fixed sigma 1 square, sigma 2 square, and a fixed m. With that, we come to the end of the module on Gaussian distribution. As I told you, I am not giving you extended set of lectures in probability theory. One topic in probability theory I chose is to be able to describe many of the beautiful properties of Gaussian distribution, and that's what this module has accomplished. Thank you very much. Bye.